Okay, so last time we also talked about this kind of angle idea, and where we had an initial side, some angle alpha. Remember, this is also Greek. HA, which I use a lot. I can't remember if the book uses it. It probably does in places. And this is the terminal side, and let's see if I can spell it today. Terminal. And I think that's right, so that's good. The relationship between an initial and terminal side is that the initial side gets laid down on the x-axis, right? Here's the y-axis, the x-axis. And basically the terminal side hangs out wherever it is. You're going to see in the next chapter there's something called a central angle of theta radians. A central angle is some angle that's between 0, here's theta, and 2 pi, which is the same as 0 theta less than equal to 360 degrees. It's much better to start thinking in terms of radians. But, I mean, I see them, it's like two languages I speak. I see degrees and radians at the same time. Like if you speak Yupik and English, you can probably hear my translation in your head in two different ways. This is the one that's important though. So what was I just talking about? The next thing's going to talk about a central angle. The central angle is the angle that if you take this and the angle is between 0 and 360 degrees, or 0 and 2 pi, and lay it down on the x-axis, open it up like it's supposed to, it looks like this. This is the central angle of radians, which intercepts an arc length. Okay, so this is one reason why people are pretty turned off by math. I think this is a direct quote out of the book here, which who knows if you guys are using this. This will be used in the future as well, and they may be using different books, but I swear it all has verbiage like this. Consider a circle of radius r and an angle of theta radians as shown in 6.11, which is more or less this. The sides of the angle of theta radians determine an arc length s on the circle. What are they talking about? The sides of this determine this arc length on the circle. That's not so bad. There's s is our arc length. We will say that the central angle of theta radians intercepts an arc of length s on the circle, or that an arc of length s is intercepted by the central angle of theta radians. I'm going to say that one more time because I didn't even understand what that was. The use of language in these books sometimes is very weird, and you kind of have to work it a little bit to see what they're talking about. One more time. We say that the central angle, actually maybe I'll point as I'm reading, we say that the central angle of theta radians intercepts an arc of length s, so it intercepts this. Basically, it's defining this on the circle and is intercepted, or we say that the arc of length s, it'd help if I could read, s is intercepted by the central angle of theta radians. Once again, that's absolutely awful use of language in my own idea. Here's what they're saying. You have this central angle. Here is some generic, so here's an angle, here's theta. Basically what they're saying is if you put this in a unit circle, or any kind of circle, it's going to cut out this part, which is the arc length here. And that's the only thing that they're really trying to get at here. So if you're reading this, and please do read your book, as poorly written as they are, it's very important to read your book. But if you're reading this and you don't get this, just kind of keep going through it. So we already talked about how theta was defined. We know that theta is equal to s over r. That means this arc length is equal to theta times r. And this is a practical formula for figuring out distance if we have it. Let me see if okay, so we have some examples here that I ended up writing down. example number 1, it says find the length of an arc of a circle of radius 8 foot that is intercepted by a central angle of 2.3 radians. Okay, so first off, anytime you're doing problems like this and you can draw a picture, draw a picture. I'm going to leave this one alone for a little bit, and I'm just going to draw a generic picture like that. So what did I just learn about this problem? I learned that the radius is 8 feet. So here's my radius. This is 8 feet. And so this is a generic radius. And what do I have? I have a central angle of 2.3 radians. Okay, so this central angle is 2.3 radians. It'd be good if I started drawing this about right. Remember, 1 radian was 57 degrees and some change. So 2 point some odd radians. What did they say? 2.3 radians? 2.3 radians. This has got to be like more than 100 degrees. And why am I going on about this? It's oftentimes very, very handy if you can draw a semi-accurate picture. In this case, here is this piece, 2.3 radians. I know this is, something like 100 plus degrees. I could find out exactly, but I'm being lazy, and I don't need it for the picture. I just want to know. Here's 90 degrees, so I'm just going to put it like this. And so here is this angle, here is theta, and we're given that this is, in fact, 2.3 radians. And I'm writing radians now because pi isn't in there. And this is one of these things, this is about usage. If I write pi, and we're talking in terms of theta, this is obvious that this is radians. I hope it's obvious. If I write 2.3, I will almost always write radians simply because the pi doesn't show up. Yeah, it's like I before E except after C, except in Einstein and stuff like that. Yeah, you're supposed to go a little crazy. Anyway, why am I yammering on like this? Well, we have this problem. Incidentally, so I'm drawing a picture. I know this radius is 8 foot. Here's this arc length, S. I also know that S is equal to theta times R. Now I suppose I better find out what they actually want me to figure out. A, find the length of the arc of a circle of radius 8 feet that is intercepted by a central angle of 2.3 radians. This is what they want. They want to find the arc length. Well, now I'm doing well because I already know that S is equal to theta, which was given by 2.3, times the radius, which is 8 foot. And I did this computations. It's simple. I used my calculator, though, because I'm lazy today. This is 18.4 feet. And I guess I'll put it over here, 18.4 feet. Think about what would have happened if this was in degrees. This is why degrees doesn't work anymore. This in radians is a scalar. It doesn't actually have any units attached to it. It's not feet, inches, or anything else. It's just a number that tells you, size in a way. Scale, for that matter. Suppose this was like 100 degrees. Does this make sense? That S, which is in fact, this is a length. This is arc length. This is length. This has feet, inches, something like that. This is going to be 100 degrees times 8 feet. This would say this is 800 feet degrees. And that just doesn't really make any sense for what we're doing. And this is why this notion of radian measure has come in and why it's so handy. There is another question on here. It says, find the length of an arc of a circle of radius 12 inches that is intercepted by a central angle of 60 degrees. It's a little more difficult. And incidentally, I strongly recommend that anytime, these are word problems. I mean, almost a lot of your trig is going to be word problems, which I know all of you really like. Anytime, how do you successfully navigate word problems? First thing, always read them again. Read them 3 times. Let me get rid of some of this junk.